We also have ray tracing rules that we can use for mirrors. Just like how we had ray tracing rules we can use for lenses, we have them for mirrors too. And there's some different sets of rules for whether your mirror is converging or diverging, and they kind of follow along the same pattern as our ray tracing rules do for thin lenses. We are not going to play with mirrors at all in lab. We are going to play with thin lenses, and we are going to do ray tracing for thin lenses in lab, but we're not going to do ray tracing for mirrors in lab either. So I have the rules here. In class, if we were together, I would have us work on an activity in lecture where we would practice the ray tracing. So instead, what I'm going to do is I'm going to do the ray tracing when I solve some problems with convex and concave mirrors. So you can see those ray tracing activities in action together with the numerical calculations for the problems. We're going to do two problems where we practice the ray tracing and also calculate the magnification of an image produced by a concave mirror, and then the next one will be a convex mirror.
Here we're going to practice a concave converging mirror with an object located inside the focal length. Okay, so here's our concave mirror. So it's opening kind of like a cave. Okay, that's kind of how I think about it. I've got my radius of curvature right here. So the radius of curvature is twice the focal length of our mirror, or you could say that the focal length is half of the radius of curvature of your mirror. Okay, so we are going to place an object 8 centimeters in front of a concave mirror with a focal length of 14 centimeters. What is the magnification? Okay, so our knowns and unknowns. Okay, we have DO, that's the distance that our object is away from the mirror. That's 8 centimeters. And the focal length of our mirror is 14 centimeters. So when we have a concave mirror, our focal length is positive. Okay, what is the magnification? So we're looking for magnification equals question mark. So our equation for magnification, we can write it as minus di over do. We can also relate it to the height of our image, but we're already given do, so we might as well get di, the distance that our image is away from the mirror, in order for us to figure out this magnification. Okay, so let's go ahead and, so I've drawn out my sketch here. Here's my mirror. This is the midpoint down the center of the mirror. I've got my object at 8 centimeters in front of the concave mirror. So this focal length is 14 centimeters. My object is somewhere right inside here. So here I'm going to draw my object. And then this distance here is 8 centimeters. That's our DO. Okay, and we're looking for distance that our image is away from our mirror so we can get the magnification. We are going to do the ray tracing for this problem just to practice ray tracing before we get the numerical value for the magnification. Just helps us sort of get our bearings, get an estimate of where that image is going to be located. Now for a concave mirror like this, our image is real if the distance that the object is away from the mirror is greater than the focal length. Real for a mirror means that that image appears on the same side as the object. That's opposite of our convention for thin lenses. For a mirror, we have a virtual image for this concave mirror. We have a virtual image if the distance that the object is away from the mirror is less than the focal length. And for mirrors, virtual means that our image appears on the opposite side of the mirror as the object, which is different, again, from our thin lens convention. So let's use our ray tracing rules for spherical mirrors to get an estimate first of where this image is going to appear. So for our ray tracing rules for spherical mirrors, our first rule, a ray approaching a concave converging mirror parallel to its axis is reflected through the focal point of the mirror on the same side. Okay, so what does that mean? I'm going to draw my ray parallel to the axis here, and then that ray is going to be reflected through the focal point of the mirror on the same side. So it's going to be reflected through my focal point. Now, when we know we're going to have a virtual image, okay, like this one here. Whoops, I was a little bit off. When we know we're going to have a virtual image like this one here, I'm going to make a dotted line that projects me over onto the opposite side of my mirror, because I know my image is going to appear over here since we're going to have a virtual image. Okay, so this is 1, where our ray is parallel to the axis, and then it gets reflected through the front focal point. And I've got my extension of that ray on this side because we're going to end up with a virtual image over here. That's 1. The next rule, a ray approaching, and this is actually the third rule for concave lenses. I'm skipping to the third one. A ray approaching a concave converging mirror through its focal point is reflected parallel to its axis. So how do we do that? Okay, so we're going to have a ray that is going to leave this object, and we're going to imagine that that ray is leaving through the focal point. Okay, so here's the focal point. I'm going to draw my ray passing through the focal point here. It's going to get reflected here off of my mirror in this direction. And then I've got my dotted extension back here because we're going to have a virtual image. Oh, I need to extend this one a little bit further. Okay, there we go. So this is actually my third rule for mirrors. Did that one before I do the second rule, because the second rule is always the one that's harder for me to do without a protractor. Okay, and the second rule for both, it's the same for both converging and diverging mirrors. A ray striking the center of a mirror is followed by applying the law of reflection. It makes the same angle with the axis when leaving as when approaching. So that means that my ray leaving my object is going to come to the center of the mirror. And with our law of reflection, our incident angle is the same as our reflected angle. So if I took my protractor right here, I can figure out exactly where this reflected angle should be. So this angle right here should be the same as my reflected angle right here. Let's see how well I can do. Looks about right. I'm just eyeballing it here. Okay. And then here's my extension back to this side because we have a virtual image. All right. This is our second ray. So over here where these dotted lines converge, that's where my image for this problem appears. My image is going to appear over here. Okay, so it looks like my image is going to be larger, it's going to be magnified than my original object, and it's going to be upright. So let's test that with the numerical calculations. To get at the magnification, we have to find the distance that our image is away from the mirror. We've already know what the distance our object is away from the mirror. That was a given. So now we have to find this distance right here. This is di. Okay, so I will use my thin lens equation. 1 over f equals 1 over do plus 1 over di. I want to solve this equation for di, so I'm going to move do to the other side. So 1 over di equals 1 over f minus 1 over do. And that equals 1 over the focal length was 14 centimeters minus 1 over the distance our object is away from the mirror, which is 8 centimeters. Okay, so then this gives us 1 over di equals minus 5.36 times 10 to the minus 2 inverse centimeters. So remember, we've got 1 over di. We want to get di, the distance our image is away from the mirror. So we have to take the inverse of both sides. If we take the inverse of this side, we'll get di. If we take 1 over this number, then that will tell us the distance that our image is away from the object. And so if I do 1 over this number, I get minus 18.7 centimeters is the distance my image is away from my mirror. And this minus sign means for a mirror, we're on the opposite side of the mirror, so we have a virtual image. And that is exactly what we have here. Remember, this is the opposite convention for thin lenses. For thin lenses, if di, the distance our image is away from the lens, is negative, then our image is on the same side as the object. So the rules for that are flipped for mirrors. Now to get the magnification, magnification equals minus di over do equals minus negative 18.7 centimeters over do, which was 8 centimeters. The units of centimeters cancel on top and bottom, and then I find that my magnification is positive 2.33. So my image is upright, that's the positive, the same orientation as my object, and I've enlarged my object by a factor of 2 1/3, essentially. So I could actually come in here and measure the heights of these and find out if I've actually done that. So maybe let's do that, because we haven't done that really before. So this object here is about 5 centimeters. Okay, so HO is about 5 centimeters. Then we'll measure the height of our image. The height of my image is about 15 centimeters. Okay, so 15 divided by 5, that's 3. So you could also find the magnification is equal to the height of the image over the height of the object. And that's here, 15 centimeters over 5 centimeters. So that's telling me that from my ray tracing here, my magnification should be about 3. But I wasn't perfectly precise here on the board, and I had to use this ruler and kind of do things vertically, but that's still pretty close to my 2 1/3 magnification. We have 2 types of mirrors. We've got the concave converging mirrors and the convex diverging mirrors. Here we are going to work through a problem where we have a convex diverging mirror. Our object is going to appear, or is going to be placed on this side. So we've got the spherical part bulging outward toward the object with our convex mirror. Okay, so we're going to place an object 53 centimeters in front of our convex mirror. DO is 53 centimeters. And my convex mirror has a focal length of 26 centimeters. Now the convention is if you have a convex mirror, it has a negative focal length. So just like how we have a diverging lens has a negative focal length, the convex mirrors, which are diverging mirrors, also have negative focal length, okay? What is the magnification for this system? Magnification equals question mark, and just like what we did, in order to get the magnification, we are going to have to figure out what the distance that the image is away from the mirror. So remember, magnification is equal to minus di over do. We already know do, the distance our object is away from the mirror, so we have to get di, the distance our image is away from the mirror. For a convex diverging mirror, we always have a virtual image. So if we place our object over here, we're always going to get an image on the opposite side of the mirror. That's our virtual image for mirrors, okay? Twice the focal length is 52 centimeters, so our object is just outside that. So I'm going to place my object right here. If this is the focal length, this is twice the focal length. I'm going to place my object right here, okay? And it's located at a distance of 53 centimeters away. That's what we said DO was. Okay, so the first thing I'm going to do, again, is I'm going to do the ray tracing to practice ray tracing rules for a convex mirror. All right, so our first rule for a convex diverging mirror is that a ray approaching our mirror parallel to the axis is reflected, so it seems to come from the focal point behind the mirror. Okay, so we're going to approach parallel to the axis, like this, strike the surface, oops, here, and we're going to get reflected, and that reflected ray is as if that reflected ray is reflecting from the focal point on the other side. Okay, and then since I know this is a virtual image, I've got to do the dotted line back here on the other side as an extension of this reflected line. Okay, so that's my first ray. I'm going to skip the second one, go to the third rule for my diverging mirror. A ray approaching my diverging mirror by heading toward its focal point on the opposite side is reflected parallel to the axis. So my ray is going to do this. It is going to leave the object. It's going to want to travel and appear as if it's going to pass through this focal point back here, okay? But instead it's going to reflect parallel to this axis. All right, so then I have to draw my extension back through here. Okay, actually this line that I drew first for my third ray, we don't need, okay, on that side. So it's the extension of my reflected ray back on the other side. That's what's important. So that's my third ray for the ray tracing rules. The second rule that I skipped here is the same for ray tracing for both a convex and a concave mirror. Same rule for both our diverging and converging mirrors. And that rule is that a ray striking the center of the mirror is followed by applying the law of reflection. And it makes the same angle with the axis when leaving as when approaching. All right, so my ray is going to come in toward the center of my mirror. It's going to strike right here. And so its incident angle is going to be the same as its reflected angle. Okay, so I'm going to be reflected right around here. Oops. And then for my virtual image, I've got to draw this dotted line extension on the back side. Okay, so that's my second ray. So all of these rays are going to converge on, all those lines are converging on the opposite side of the mirror as the object at one point. And so that's going to be where the tip of my image appears. So this is my image of the object that we placed over here, okay? And so we already said that convex diverging mirrors always produce virtual images. We have a virtual image right here, and we see that it's actually smaller than our original image. So we shrunk our image down. Our magnification should be smaller than 1. So let's go ahead and check what that magnification is numerically. All right, so we will apply the thin lens equation. 1 over f equals 1 over di plus 1 over do. I need to solve for the distance that our image is away from the mirror so I can get the magnification. So I'm going to move this term to the other side. 1 over di equals 1 over f minus 1 over do. And that's equal to 1 over our convex diverging mirrors always have a negative focal length. So we've got negative 26 centimeters here minus 1 over do is 53 centimeters. Okay, so we've got 1 over negative 26 minus 1 over 53. And that's going to give us 1 over di equals minus 5.73 times 10 to the minus 2 inverse centimeters. And so remember that to get rid of this reciprocal, to go from 1 over di to di, we have to take 1 over both sides. So di is equal to 1 over minus 57.3 times 10 to the minus 2, and that's going to give us minus 17.4 centimeters. So this minus sign means that our image is virtual. It appears on the opposite side of the mirror as our object. Remember, that rule is flipped from what we have with thin lenses. And we did okay with our ray tracing here, at least to get di, because the focal length is 26 centimeters. My image here appears closer to the mirror than our 26 centimeters. So, you know, we're pretty close with our ray tracing in this case. And then our magnification is going to be minus di over do. So that's going to equal minus my negative 17.4 centimeters over 53 centimeters. So the centimeters cancel on top and bottom, and that gives me a magnification of 0.33. So my image here should be 1/3 the size of my object. And it's, well, we're probably fairly close to that here. It's positive, that magnification, so that means that my image is the same orientation as my object.